Alright, chapter 13. Second to last chapter of the year. Whoa! So, let's do a quick overview. We got basically two bigger, main, littler concepts, if that makes any sense. Hopefully it doesn't. They are gravitational force and gravitational energy. So for gravitational force, we have a general expression for force. Fg, force of gravity, equals big G m1 m2 over d squared. So to have the well, I'll talk about that later. And then you can get the acceleration due to gravity on any surface or at any location with just a slight tweaking of this equation. You just basically get rid of 1m, and I'll show you how to do that later on in the video. The radius of our wonderful planet Earth is this, and the altitude, meaning the height above the surface, is your d, distance from the center, minus the radius of the Earth. I'll talk about that in more detail too. Shell theorem, pretty cool theorem. It allows you to figure out, for example, like G underneath the surface of a planet. It's basically saying that a uniform shell of matter exerts no net gravitational force on a particle located inside of it. So if you're down inside of a planet, then all of the earth and dirt and crap up above you does not exert a gravitational force on you. That's if, by the way, the density of the planet you're in, or the material above you, is uniform, which is not the case in real life. Density, by the way, is mass divided by volume. That's what this equation says. And the volume of a sphere, such as a planet, is, can't really see the divide sign, can you? 4/3 pi r cubed. Let me just fix that real quick. There we go. And then we move on to gravitational energy. We've talked about that before, but not quite in this detail. Gravitational potential energy, we've seen before as mgh, but it also equals gmm over d. We got rid of the squared, and that's just a little calculus thing that I'll show you in a sec. We got kinetic energy, which normally we think of as 1/2 mv squared, but if you deal with it in terms of the potential energy, it takes this form. And then you can use conservation of energy to talk about your escape velocity, and it turns out to be the square root of 2gm. This, by the way, is the m of the planet, not your mass, divided by r, which is the radius of the planet, or the distance of the planet, distance from the center of the planet that you launch at. So that's the main overview. Let's get into more detail. Alright, so Newton's law of gravity, Fg equals gmm over d squared, is an inverse square relationship, basically stating that the farther first off, you need two masses interacting to have a gravitational force, and we call them m1 and m2, but you can change the subscripts to be like Earth and Sun or whatever you want. But the farther apart these two masses get, according to this relationship, the weaker the force, and vice versa. The closer they get, the stronger the force. The larger the mass, the stronger the force, and the smaller the mass, the weaker the force. So that partially explains why when you're standing next to someone, you don't just collide into each other because of an intensely strong gravitational pull between the two of you. It's because your masses are, on the grand scheme of things, quite small, so the gravitational force is not enough to overcome, let's say, the friction of the ground holding you at your location. So G, by the way, is gravitational constant, 6.67 times 10 to the negative 11. If you look in your book, it goes to, on the back cover of your book, it goes to one more decimal point, 6.673 times 10 to the negative 11. And an interesting thing about science, at least in terms of astronomy, is the fact that we have to make some assumptions. We assume that the laws of physics, as we see them here, behave the same in all of our visible universe, and so, at least the part of the universe we can see. And so, under that assumption, we would assume that big G is the same everywhere. And so that's how we've come to explain the phenomena that we've seen with, for example, the Hubble telescope way out in deep space. Now, is this actually the case? Are the laws of physics substantially different? Probably not. Slightly different? Don't know for sure. Most likely, though, it's not that they would be different. It's just that things are going on out there that we just don't know enough about yet to make valid theories, so that it may appear as though the laws of physics are different out there, but it's just something that we don't know. So anyway, cool little aside. But so this is a force, right? So if you how do you find the acceleration due to gravity? For example, we've used plenty of times that little g on the Earth is stop. Little g on the Earth. All right, undo, pause. All right, gosh. Little g on the surface of the Earth is 9.8 meters per second squared. Where does that come from? Well, it comes from this. We basically say that the net force acting on you. So here's part of the Earth, and here's you. The net force acting on you is just gravity, we'll say. So F net equals ma equals, and then just there's only one force, Fg, which is g m1 m2 over d squared. So if you're on the Earth, this is basically the net force on you, so we'll say mu times g, which is the acceleration due to gravity, so it's still acceleration, we just call it g, equals big G, 6.673 times 10 to the negative 11, times the mass of you, times, you're on the Earth, so the mass of the Earth over the radius of the Earth. Let's be consistent here. Squared, because you are that far from the center of the Earth, the radius of the Earth. And these cancel, and you get G equals gm over d squared, where 1 here would be the Earth if you're on the Earth, or maybe a little m if you're on the Moon. D would be the radius of the Moon or the Earth or wherever you are. And this doesn't even have to be on the surface. This could be anywhere in space. So as you can see, if you get farther from the Earth, the acceleration due to gravity would decrease. This does not explain, for example, why astronauts appear weightless on the space station. In fact, they are not weightless. What's happening is they are just in free fall at the same speed as the space station's at free fall, so it appears as though they're weightless because they're falling at the same rate as the space station. And then why doesn't the space station crash? And why don't they crash if they're falling? It's because as they're falling, they're orbiting tangentially, moving tangentially to the Earth fast enough to keep them at a constant height. Right? And if they're moving that fast and they weren't being pulled towards the Earth, then they wouldn't orbit. They would just go straight off into space. Right? So it's a combination of tangential motion and radial motion that keeps them in orbit. So yeah, so that's how you find the g of any planetary surface. So for here, 6.67 e to the negative 11. Mass of the Earth is was it 6 mass of the Earth? 5.98 times 10 to the 24 kilograms. I'm looking, by the way, at the back cover of our textbook. And the radius of the Earth is 6.37 times 10 to the 6 meters. So you plug those numbers in, and you'll get 9.8. I won't do that out. Take too much time. All right, and so yeah, I just stated this. So this is the radius of the Earth. So in some problems, for example, you're going to have to deal with not being on the surface at some like altitude above the surface, right? So my variables and the labeling here are not consistent, so I'm going to just change this to a d, where d is the distance from the center, and then re is the radius of the Earth. So your altitude here's the surface of the Earth. Your altitude is this distance, your height above the surface. So you just subtract d and re and you get the altitude. So that's all I wanted to say for that, because you'll need that for some problems. And the shell theorem. So you might have heard before at some point that if there was a tunnel straight through the Earth and you're able to fall through the Earth, that you'd be weightless at the center. And you can probably imagine why, because you got all of the mass of the Earth on this side pulling you up, canceled by all the mass on this side of the Earth pulling you down, and then here cancels here, here cancels here, here cancels here. Basically everything cancels, and so you're weightless here. That is the fundamental sort of logic behind the shell theorem, which states that, so here's like the shell of the Earth. So if you happen to be right here inside the Earth at this depth below the surface, all of this material in this shell here, oops, all this material exerts no gravitational force on you because everything cancels out. You might be thinking, wait, but you're closer here to this mass than you are here, so wouldn't this exert a stronger force gravitationally than this? Yes, but look at how much is close to you. Maybe this much is super close. How much is super far from you? Oh, this is super far. So you have more mass that's super far away than you have mass that's close, and as long as the density of this material is uniform, then it will all cancel out perfectly. Density is mass divided by volume, and so you're going to need that for some of the problems. And since planets are spherical in shape, you'll need the volume of a sphere, which is 4/3 pi r cubed. And the minus sign disappeared, but I fixed it mid-sentence. That was pretty crazy. Yeah, so that's all I wanted to say for that. Again, I'm going through these sort of quickly, but a lot of these will become clear when I do sample problems. Gravitational energy. So I'm going to do this in a second video, and probably neither video will come close to 15 minutes. This one's 12 and a half. So yeah, I'll continue main concept 2 in the next video.
See ya.